correspond to the previous impulses, all will get added, and sometimes constructively, sometimes destructively. So there is going to be a. So this phenomenon is going to cause what is known as multipath fading. It means normally, signal some power is transmitted from here, but what is received will be less because the signal has traveled distance. That is called a propagation loss. Okay, there is a channel is very wide, then the loss is measurable. It is not going to change with respect to time, and it causes what is known as attenuation. So attenuation means what? If I transmit a sine wave like this, attenuated one will look like this. Same thing, sorry, my drawing may not be that appropriate, but the same thing, reduced amplitude. This is, say, let us A minus A. This may be A by 3, for example, A by 2 minus A by 2, let us say. So, A was transmitted, A by 2 was received. No problem. If this is the case, then we know how to amplify and then deal with it. Yet another case could be like this. So this is the sine wave I transmitted. If there was simple attenuation, I will receive like this, easy to handle, easy to amplify and do things. But because of the multipath phenomenon, there is going to be sometimes a reduced amplitude, sometimes more amplitude, still less, different. So this is called fading. This is called faded signal. This is attenuation. Okay. This is attenuation. And this is fading. So if such a waveform is received, then what will I get? This is all we assume that in this period it has got multipath delay also. So this is what is received. Therefore, you can now imagine what is the effect of this multiple path effect, and how to detect the bit that was represented using this waveform. Okay. So now, on top of this, there is noise also. Okay. So now, how do we measure the performance of the system in presence of a multipath phenomenon like this at the receiver? So let me just give you an idea of how performance is measured in digital communication, and then how this kind of an effect is going to cause serious degradation. Normally, in digital communication, the performance is measured using what is known as energy per bit per dB with respect to bit error rate. Okay? So 10 power minus 5, minus 4, minus 3, minus 1, so on goes. So 0, let us say 2, 4. So what people do is transmitter, then channel, then receiver, and this output. This is the output. Now, at this output, as we pointed out earlier, the quality of service is to be delivered. That means without any loss, okay, without any error, you have to deliver depending upon what type of traffic you are dealing with. But let us say voice, we are dealing with voice. For voice, we said that 1 error in 10 power 5 bits are accepted. So to get this kind of a quality, what is the EB by N naught that is received, to be received at the input of the receiver? EB by N naught, energy per bit per EB is the energy, which is the signal power and the bit duration, divided by N naught. N naught is noise power is N naught into B. That means B is the bandwidth, this is the watts per hertz in the channel that one experiences. So if you happen to know these values, this KT, K is Boltzmann constant, T is the temperature at which you are operating, all this can be calculated. And T is the TB is said to be derived from the bit rate, okay? And AC is the signal that is received here. So you require to receive. Let us say, with respect to, you go on increasing this EB by N naught. That means you transmit a particular power from here, a particular AC is received here, you know TB, you know N naught. So, corresponding to what is transmitted, something is received. So, you measure that EB by N naught at the receiver input, and correspondingly, what is the bit error, you find out. Then again, you increase this transmitting power. Then again, you find EB is different. So, if one plots, is something like this, for example. As you increase, as you get the EB by N naught at the input of the receiver higher and higher, there will be better signal power you will be getting, or noise is less, whichever is the proposition. The bit error rate also will go on decreasing. This is in presence of BPSK modulation, okay, in presence of AWG only. If there was only noise, if we have used a BPSK modulation, the performance of the system in presence of only noise will be like this. As we, even at 9.6, let us say 10 dB, even at 10 dB, you will get 10 power minus 5. Just to give you a rough idea about what will happen if there is a fading, it will like this. Even worse than this, but I am just showing you for some comparison. Okay? To get 10 power minus 5, 1 error in 10 power 5 makes you require to receive more than 30 dB EB by N naught at the input of the receiver. In other words, you should have transmitted much higher power in order to give you that type of EB by N naught at the input of the receiver. So, it is making the performance so worse. It requires very high power to be transmitted, signal power to be transmitted in order to handle the fading, this phenomenon. Okay? So, which is not possible. In a mobile communication, you can't indiscriminately increase the power. Mobile communication, the transmitters are transmitting only less than a milliwatt of the power. So, in that case, it is not possible. So, this is the kind of degradation that the signal experiences, BPSK, in fading channel. Okay? In fading channel. So now we can imagine how worse this performance is. To get the same output quality, one system, the same system, only noise requires only 10 dB, whereas the same system, to get the same quality in a fading channel, it requires 30 dB or even more than 40 dB at least. 30 dB, even 20 dB more. 20 dB more means what? 100 times more. It even sometimes 40 dB more. 1000 times more signal power is required to get the same quality using the same modulation when there is fading present. And this fading also, this also is random. Sometimes you for one bit experience this kind of a fading. Another bit will experience a different type of fading. So because it is a time variant system. Okay? So time variant phenomenon, and that is still this is average. This behavior is an average behavior. So on an average, this performs like this. But when you look at the instantaneous behavior of this channel, you will find that it's quite challenging to deal with. So this is how the wireless channel is going to affect the performance of the digital receiver, and we require a lot of technologies, complicated technologies to deal with it. Now, to just mention one technology, we know on error control coding, as I told you. So for example, at 15 dB bit error rate, at 10 dB, let us say here 10 dB bit error rate 10 power minus 5. In this case, the bit error rate is 10 power minus 2. So in one case, if you look at the same transmitted power, in this case, if there was only noise, it was 10 power minus 5. When there is fading also, it is 10 power minus 2, let us say. Now, how to bring this 10 power minus 2 to 10 power minus 5? This is one error in 100 bits. You want to bring it down to one error in 1 lakh bits. What can we do? We can employ error control coding. So you employ a powerful error control coding to bring down this error, to transmit the same power, but this error can be brought down if you have powerful error control coding. Then this curve can be moved this side. For example, I just tell you like this. Okay? Same BPSK, fading channel with forward error correction, let us say, with error control coding. So this curve can be moved this side. So what are we saying? We have spent bandwidth. We have spent extra bandwidth to deal with this kind of a phenomenon. This is happening in the wireless channel. We require to deliver a quality at the receiver. To deliver that quality, we find you have to transmit enormous power, which is not possible. And in order to come out of that situation, in order to deal with that situation, we wanted to introduce error control coding and brought the errors to the minimum level and saved the power, but we spent extra bandwidth. So this ultimately is driving us to spend extra bandwidth. But in wireless channel, if because of this fading, if we are spending extra bandwidth, then we also need to find bandwidth for transmitting higher bitrate sources, higher bitrate traffic, and then you want to add, these days it's a multimedia traffic and even Internet of Things. Many 50 billion devices are going to be connected across the network. If such a thing is happening, then we need to find bandwidth for all these purposes. So it is also required that bandwidth is to be very carefully used, and you have to save the bandwidth also. So you need to save power, you need to save bandwidth. So the constraint here is very stringent. Okay, both the power and the bandwidth should be saved, but the complexity of the system can be as much as one can think of. As you see, cell phone is a very complicated electronic system which provides you this kind of very effective communication through wireless channel at very high bit rates also. But with the battery operated device, okay, by transmitting less than a milliwatt power, you are able to get the communication done. So, what are all the techniques that are incorporated? We have mentioned one modulation, one error control coding, one equalization. Now, these are some of the system. Other than that, we still have some other things we will come back later. But then, what are all the frequencies that are used in wireless communication? And every generation of the wireless communication, how the bandwidth is assigned for various services, and how the bit rate is brought down for a required service. And so bandwidth and the bit rate are related. So the question is, as we told, for 1 hertz of the bandwidth that you spend, we want to transmit as many bits per second as possible. So then we should also bring down the bits per second that is required to be transmitted. So then we can save the bandwidth also. So in that case, we require what is known as source coding, which is essentially a compression scheme. Voice can be compressed, video can be compressed by exploiting certain properties of the signals. So this is a subject by itself. A lot of schemes are available. People is a more or less mature subject, and from the research that has been already conducted, people have chosen in standardization process certain bit rates for voice and bit rates for video and so on. We will come to those issues, the specifics later on. So what I wanted to bring in here is the wireless channel is quite complicated channel, quite a challenging channel, which introduces effects which are very difficult to handle, and for which our resources have to be very carefully used. And that's what is the purpose here. We have tried to interlink the processes that are happening in the wireless channel with the techniques and technologies that we are using to effectively communicate across the channel. And then along with this, there is networking issues. So networking issue we are not still brought here. So now, what we can understand is that a wireless channel, particularly in a multipath environment, at the receiver, the signal is getting attenuated, but attenuation is also time varying attenuation. And at the receiver, there is a delayed response. It's called a multipath delay. Okay? So that delayed response is going to interfere with the subsequent bits, subsequent signals, which is another phenomenon. Already signal is getting attenuated, very small strength signal will receive, and that signal is also varying in nature. And the delay is also varying in nature, and delay dispersion is very high. And one other phenomenon, because of the mobility of the transmitter, the receiver, because when you are mobile, you are transmitting as well as receiving. Because of the mobility, one other effect is taking place. That is called the Doppler effect. Okay, another important issue is called the Doppler effect. So, I will show it here. So, Doppler effect. Because of Doppler effect, what is meant is, you find, depending upon the velocity and the frequency that you are using, the frequency you are transmitting at a particular frequency. So corresponding wavelength can be calculated. Suppose I am transmitting my carrier frequency is 900 megahertz, for example. So this FC C equal to FC lambda. Okay, so implies lambda equal to C by FC. You can calculate C is velocity of light, FC you can calculate, substitute here. Suppose the mobile is moving at a particular speed. So then what happens is, there is what is known as a Doppler shift. You transmitted at 900 megahertz, but what you will receive is 900 megahertz plus this FD, FC plus FD if the mobile is moving towards the base station. Okay? So what you will receive is FC plus FD or FC minus FD. This is mobile is moving towards, the mobile is moving away the base station. So this is in effect introducing what is known as a frequency modulation. Here we said amplitude is getting increased, decreased, and it is a time varying phenomenon, quite complicated, and we need to deal with it, so we have to understand that. Another effect, because of the mobility of the receiver transmitting mobiles, what happens is, depending upon the velocity with which it is moving, depending upon the frequency of operation that you are in, we find the received signal is either getting higher frequency or lower frequency than what you have transmitted. So what is the effect here? So this effect will be frequency modulation is taking place, which will cause certain degradation in the performance of the system. So correspondingly there will be errors. So errors will be more. In order to handle this effect, it is called frequency dispersion. One is time dispersion. In the previous case, one impulse is dispersed over time for this much time, and in this case, one frequency that you have transmitted is is smeared like this. Suppose if you look at the spectrum, you transmitted a spectrum like this. So the effect of Doppler shift will be, it will be so it will be something like this. You will receive a spectrum like that. So sometimes the frequency will be more, sometimes the frequency will be less. But your signal you transmit only in this band. But what you would have received is in this band. So this is how this is frequency. Okay, this is frequency and this is amplitude, whatever is. So you transmitted in this band a wireless signal, but what you receive is in this band because the additional subtraction of this frequency that you have transmitted, and how to handle this. This will cause error, and so this is another effect. So three important effects. One is the amplitude of received signal is very small and time varying. Number two, it is experiencing dispersion, time dispersion, and because of this is causing intersymbol interference. And third one is the Doppler effect, because of the speed with which the mobiles are moving. Not only the mobile, but also the other structures which are moving. The multipath is from various obstructions. The obstructions could also move, and because of that movement also there is going to be a Doppler effect, and that is all experienced like this. Now what is this? You transmitted only this, you are supposed to confine yourself in this bandwidth, but unfortunately your signal is going to this. Okay, just 1 minute. I will bring in another effect. So normally any frequency spectrum, this is a frequency, this is one particular band for a particular application. You know that the electromagnetic spectrum is divided into various bands, and each band is given to various applications depending upon the type of requirement. So suppose this is the bandwidth that is allocated for mobile band, let's say, wireless communication. and somebody has purchased this band, and this is divided into okay, this is I divide this into two, okay, two bands. This is one person or one organization has purchased. This is another organization has purchased. So this particular person, what they will do is they will divide this into 1, 2, 3, some 100, whatever, depending on what is the requirement. So like this. Okay. So this is 1, 2, 3 like this. So this is one channel is transmitted through this band, another channel is transmitted through this band, and so on. So when I transmit through this band, I am supposed to confine only in this band. When I transmit through the transmitter till the receiver, I should only occupy that band. This has to occupy this band, this band. Of course, ideally speaking, like this, but there will be what is known as a guard band. Because தனியாக சொல்லுங்கள், கன்ஃபியூஸ் பண்ணுறது. அதாவது இன்ட்ரெஸ்ட் காட் பேண்ட் ஸ்டாப் பண்ணுறது.